Welcome to my introduction to programming course using Python. So what are the goals of this? To learn program, you really need to know two things. One is some programming language, and for this we're going to use Python. But what's probably even more difficult is learning how to represent problems using a programming language. The programming language itself consists of syntax. There's rules, like when you learn to read and write. In an English class, you learn grammar and you learn how to spell things and things of that nature. But understanding the grammar of a language doesn't make you a professional writer. In order to write well, you have to know how to use the programming language, the spoken language in some way. So I'm going to try to teach the two of these, and my preference is to sort of interweave the two. So as we learn new programming elements, I'm going to also write code and explain the thinking process, at least as I see it, to you. Now realize that there could be many legitimate ways to write a program to do a particular task. And so they could be equally valid. Now there's situations in which you may argue one way is better than another based on some criteria, but there's going to be other situations where there could be many equally good ways of doing something. So I'll give you my opinions as we move through the course, and hopefully that will help you better understand how I think about things and in turn help you learn to program. But what is computer programming? Really all it comes down to is representation of a task or an algorithm in a computer language. So then what's an algorithm? Well, it's really just a set of directions for accomplishing some task. I can tell you that I always find it amusing when I occasionally read an article in the newspaper or online in which they talk about how someplace, like maybe at a hospital or someplace else, they're now using algorithms for things, and they always act as if it's some deep secret what an algorithm is and it's super special, but really all it is a set of directions. And there are algorithms that are famous, so algorithms itself, the study of those algorithms, is important enough that computer science majors typically take a course on trying to understand algorithms and analyzing how well they perform and things of that nature. But there's no real mystery behind what an algorithm itself is. So let's look at an example. So let's say you have some grades and you want to calculate the average of those grades. Now the way most people do it is calculate what's called the arithmetic mean, because there's actually other types of means. But for the arithmetic mean, it really comes down to this. You add all the numbers together and you divide the sum by the quantity of numbers, right? So you've probably done this yourself. In mathematical terms, we might write it using this expression. So this symbol here is a capital sigma in Greek, and so this is a summation of the terms, and we divide by n, which is the count of the number of terms, and that then gives us the average. How would I do that in Python? Well, in Python, I could do something like this. Now realize that I wouldn't expect you to already know all this. If you did, then you wouldn't be watching my videos. But this is using a number of language elements that we'll get to over the course of several videos. But I start at the top by storing the grades in what's called a list, so it's between square brackets. And then I want to count how many numbers are here, so I can use this length function, and I store the value in n. So at this point, n equals 5. And then ultimately, I want to sum these numbers up and divide by n. And to do that, I'm going to create this summing variable called mySum. And so here we have what's called a loop. And so as long as I is less than 5, I'm going to go through adding each grade to my sum and also updating I by 1 each time. And once I've once I've summed all 5 of the numbers together, then I'm going to come down and divide that sum by 5, and then I want to print it out. And when I print it out, what the program prints is average grade equals 76.60. Now one of the things that's nice about the Python language is it has lots of built-in functionality. So I wouldn't necessarily have to do all this myself. I could replace from this line from mySum equals 0 down to average by simply just writing a single line here. Because there's a built-in summing function that when given a list of grades can add them all up for me and then return whatever the sum is, and I take that sum and divide by n and store it in average. So from mySum down to right above, or actually including the average equals mySum equals n line, I can replace with a single line of code, which is one reason why Python's so popular. You can get a lot done without doing a lot of work. So why even learn stuff like this? Well, somebody had to write the summing function, right? And behind the scenes, it has to do something like this. There's no magic in programming. Even though sometimes as a programming instructor, I've said that magic happens, meaning it's taken care of for us and I don't worry about how it's done. But somebody had to know how to use the programming logic that this represents to write this function, that's what we'd call this, to do this. So if you're going to be a programmer, you need to understand this type of stuff, even though in your everyday programming you may choose to use summing functions, like I do. If I was writing code to do this and didn't care about demonstrating the logic behind it, I might just write average equals sum of grades divided by n. That's how I would do it. So let's better understand programming languages as well as programs themselves. Let's start with an example. So suppose I asked a student to come to the front of the room. At a high level, the way they accomplish that is they stand up and they walk to the front of the room, right? Seems simple enough. But if I said, well, give me more details about what you did. Well, at the next level, they might say, well, what I had to do is I stood up, I turned 90 degrees to the right, I walked 15 feet, turned 90 degrees to the left, and walked 10 feet. Okay, that's what they did, but I said, okay, give me more details. So at a lower level of abstraction, they say, well, I had to contract specific muscles in a specific order. Nobody, of course, thinks this way, but that is technically what you're doing. And then if I said, well, give me even more detailed explanation of what you did, they'd say, well, I thought about walking, which initiated many electrochemical reactions. So this is true, this is true, this is true, and this is true. So what's the point of this? Well, programming languages can be described as being high level or low level or mid level based upon how much work they do. And something like Python, which is a high level language, I can write this one line of code that does 1, 2, 3, 4, 5, 6 lines of code. But other programming languages that don't have this type of functionality would require you to do something similar to this. That's just the way they're built. But ultimately, stuff like this has to happen even if you don't think you're doing it when you write this. So if I were talking about high-level languages, I might list things like Perl or Python or MATLAB. The programming language C, which has its use, is a mid-level language. Even lower than C is something called assembly language, and lower than that is machine code. Now this is just 1, 2, 3, 4, 5, 6 languages. And some of these could be subdivided. There's lots of different flavors of assembly language, but there's literally thousands of programming languages that have been invented over the years. But this is a way of thinking about it. So people are attracted to Python because it does a lot of work for you, and I think that makes it well suited to learning how to program. These things are important. For many years I worked at a university in which I taught C and assembly language, and we mentioned machine code, but I didn't ever actually program that myself. Very few people do. But these are all tied together. But in terms of people learning to program in the first place, I think Python's a great place to start. So how do you go about writing code? Well, one of the things people struggle with most when they're trying to learn to program is how do you take a problem like finding the average and decompose that into something the computer understands. That's always difficult for people in the beginning. So the two ways that I rely upon myself most often is to either represent the problem using pseudocode, and pseudocode is just a quasi-English, if you speak English, a quasi-English representation of the problem where it sort of looks like a programming language, but it's not quite a programming language. And the other thing is to work through the underlying process using a baby version of the problem. Now, before we leave pseudocode, to give you more ideas of what that means is it's kind of like writing the outline to a paper. When people are trying to write a paper or a book or anything else, many people sit down and create an outline first. And why is that? Because initially they can't see all the details. And so by creating an outline, they're imposing some structure on what they need to do at a high level, right? They say, I'm going to do step 1, then I'm going to do step 2, then I'm going to do step 3, then step 4. And this starts to help them then see other details. And you go into as much detail in your outline as it takes for you to finally be able to sit down and write things out. Well, pseudocode is the same way. So throughout my video series, at times I will show you how I write pseudocode, because I really do use it, and then how I then turn that into programming. And then the second thing here, which I mentioned briefly a moment ago, is if I have to do something with 1,000 numbers, I don't necessarily sit down and work through all 1,000 numbers by hand, because that's the reason why I'm writing a program. But I may sit down and work with a 4-number version of the problem, trying to understand the mechanics, and then go through it and see what I actually did and turn around and write code based on that. So let's see an example of that. So I want to find the maximum value of 1,000 numbers. So to understand the process, and there could be different ways of doing this actually, but to understand one of the versions of how to do this, I may choose to do this right here. So let's see how I do that. So I'll start off by saying, okay, find the max of this set of numbers. -2, 8, 0, and 3. So it's easy as a human to look at this and go, well, it's obvious 8 is the answer. But imagine I gave you 1,000 numbers or 1,000,000 numbers. Well, then in most cases, it's not going to be so easy just to look at it and think you just automatically know the answer. You have to do some process. And ultimately, that process, I think, is going to be something similar to this. So you're going to go through looking at the numbers, and internally in your brain, you're updating as you see new maxes. So you might do something like this. You may say, okay, max initially is -2. So that's my initial value, because that was the first one I saw. And now I'm going to look at the next number. And for each number, I'm going to compare it to the previous number, or excuse me, compare it to the current max. And if it's greater than that, then that becomes the new max. So I say, well, is 8 bigger than -2? Yes. So now 8 is my current max. Now I compare 0 to that. Is 0 bigger than 8? No. Compare 3 to 8. Is 3 bigger than 8? No. Now that I'm at the end of the list, whatever the last thing is my max. And that's what I have. So in terms of pseudocode, let me say something like this. Initialize max to first value, then for each number in list or set. The word list actually means something in Python, so this isn't technically a list as I've written it, and technically it's not even a set as I've written it, but for each number in list, compare number to max if current number is greater than max, which you could argue is really what I'm doing here. From greater than max, max now equals that current number. And then when done, that's at this level, print final max. So I look at this, and since I know how to program, I go, okay, I know what this means. Initialize, create this max variable with the first value -2. For each number, I'm going through the list and asking a question. Is this number bigger than the current max? And if so, update. And I think you would agree that's what I did when I was working out by hand. So this is my baby version to help me understand the process. And now to understand the process, I can write up some pseudocode. Or in some cases, I can just sit down and sketch out the pseudocode without working through the process. Or in some cases, doing this is enough to skip the pseudocode. But some combination of those is what I typically use, at least for things I've never done before. After a while, you know how to do certain things, and when you have to repeat those things, you obviously don't sit down and figure them out again. So that's the process that I use for development. So let's talk about some basic concepts. I've used a variety of languages over the years, but every general purpose language that I've used has consisted of these basic language constructs. One is called a variable, and also statements. And so the purpose of variables is to store information. If I need to store a person's age, then I may create a variable called age and give it the initial value of that, or what that person's current age is, 43. I need some way of asking questions, that is making decisions. So for that I can use conditionals. And here's an example. If temperature's greater than 100, print is too hot. And then finally, I need to repeat processes. And for that I use loops. So if I wanted to calculate the first 1,000 prime numbers, the underlying process for detecting if a number is prime is the same. And so I just repeat that 1,000 times. So one of the things I would like you to learn to do as you write code is to write what are considered good programs. But notice I put it in quotes here because it's debatable what's considered good. The reality is what you intend to do, what your goals are, can determine what's considered good under that situation. So imagine I ask you which car is better, a Humvee or a small Toyota. Well, it's kind of a loaded question because I didn't tell you what I consider better. If I care about gas mileage, well, then I'm probably going to choose the Toyota over the Humvee. But if I'm going to go off-roading, I'm going to choose the Humvee over the Toyota. So each of those was better under certain situations. There's no one universally better thing, and the same is true of programs. You may try to achieve as many criteria that are considered good as you can, but there's going to be situations where you can't meet all criteria. So here's some things that I've chosen that I consider important when writing code, but as I just stated, you may not be able to do all these. So one of the things I promote is readability. That is, how easy is it for somebody to read your code and understand what you intended to do? And realize the person I'm talking about may actually be you in the future. I have known people who revisited their own code, say a year later, and because they didn't make any attempt to make it readable in the first place, because they thought, well, I just know what it does, at this point they forgot what it did, and they couldn't read their own code, so they just had to start from scratch. And when I taught programming courses, I even knew students who wrote code for a homework assignment that was so poorly written that even in the week in which we were writing the code, they couldn't even understand their own code. So they'd have to start over when things didn't work. So write for readability purposes. Related to that is maintainability. And what I mean by that is it's not unusual that programs either have to be changed because you want to add additional functionality later, or they have to be changed to fix a problem. Maintainable code is something that within reason you can change, and it doesn't certainly break everything. So imagine people built houses like this. They said, well, I'm going to put up all these walls, and then after the fact, I'll decide where to put windows or doors. Well, once they start cutting into the walls, that affects the underlying structure of the building. So is that really the way you should do it? Well, no. You would like to do it with an eye towards where you want the windows and doors and internal walls. Now, you may have to change some things later, and if you make a lot of changes, then it's obviously going to affect the building structure. But you at least want to do things with some eye towards things working correctly in the future. The next thing is scalability. And the two things I promote as a programming instructor are readability and scalability. Scalability has to do with if you have to do something a lot of times, how much work did you do, or how easy it is to make changes to do that. If I tell you to print the integers from 1 to 3, an easy way to do that would say print 1, then say print 2, then print 3. And by that I mean explicitly say print 1, print 2, print 3. But if I said print the integers from 1 to 1,000, do you want to have 1,000 print statements? I know I wouldn't. I'd rather use a loop that said, okay, print all the integers from 1 to 1,000 and just do it. So my loop would be something like this. For the number in the range of 1 to 1,000, print whatever the current value is. That's the easy way to do it. Portability is not really a problem with Python in general, although there are situations where it would matter. But when you're writing portable code, it's about taking code that might work here on my Linux computer and running on your Mac or running on your Windows computer. Ideally, I could take it to any of those 3 operating systems and it would still work without changes. Now, if you get into operating system specific code, well, now that's different. It's not going to work the same in all 3. But you would like to have portability. You don't have to rewrite everything every time you move it to a different computer. And the last thing I've listed here is performance. In general, that has to do with how fast the program runs or how much memory it uses or things like that. Performance matters. If you've ever watched a YouTube video and had to wait for it to download, then you know that you care about how fast things work. But for baby programs that most people write in an introductory programming class, performance is not really an issue in general. But it is possible to do things in such a poorly written way that even then you'll see a time lag. So I bring these things up so you can think about this. Now the reality is, if you're writing programs in a real world situation, you'll have to decide what's most important in terms of your situation. I have looked at people's code that was not well written in terms of readability, but I could tell they had traded readability in order to try to improve performance. That is, they collapsed a bunch of steps together, but me as the outsider reading their code, I could hardly understand what they did. But I knew they probably had done it to make things faster. So there's always trade-offs, but you need to know that these situations exist. So what about programming style? Python enforces certain programming style, but in terms of readability, here's some things I would point to. One is using comments. Comments are things that you leave in code that are there for the human reading the code, but they mean nothing to the programming processor, whether that be an interpreter or compiler. And we'll see some examples here in a moment. Another is use meaningful variable names and function names. Also, the use of white space is what you would think. How much white space do you leave between things? And then indentation. We'll talk about those. So let's talk about programming style. So here I've created a variable called age. I've used a meaningful variable name. If it really is age, I'd rather call it age than X, and then gave it an initial value. And in Python, using a pound sign like this creates a single line comment. So I could put it on this existing line, or I could put it on its own line, but each of these is fine. You can create multi-line comments by having sets of triple sets of quotes, whether it be 3 double quotes on both sides or 3 single quotes on both sides. It's fine, you just can't mix. But this allows this comment to stretch across multiple lines. Comments are there for humans, not for the computer. So let's say you had this. So imagine you encounter some code and whoever had written it said, this function calculates pi using the fast Fourier transform. If they didn't include this comment and you didn't already know that's what the program did, would you know that looking at it? I'm going to guess you wouldn't. I've actually had to use the fast Fourier transform, and even I wouldn't necessarily know what the underlying programming logic was if I encountered it. But imagine you encountered this code, age equals 10, and then the person put a comment, this variable is the age. Well, yeah, I knew that because they wrote age over here. So this is useless. There's no reason to say this is age because I used a meaningful variable name. Doing this can avoid a lot of this, but there's still times when something like this is useful. There are some people that will tell you that if you use meaningful variable names and function names, you never need to leave the actual comments. I think that's absurd because that's too extreme. But you don't need to have a comment on every line either. So you can go to extremes on either side. What about meaningful variable names? So imagine I had this code, a equals 10, b equals 5, and then while I would never really do this, right after this put c equals a plus b, or I take that back, maybe I would because maybe later on I update c to something else. But imagine 100 lines later I finally say c equals a plus b. Is this correct? Well, I don't necessarily know because this lacks context. I'd rather do something like this if I knew what the context was. Here's my labor cost, that's 10. My materials cost is 5. And then if I know something about basic business principles, I may know that the total cost is equal to labor cost plus materials. So now I can look at this and say, oh, this is the correct formula since I know what it does. Now, in some of my examples in which I don't have context, you may see I just use single variable names because I may just want to show you, well, how do you add 2 numbers together? And I may do something like this. And in fact, in a video that follows this, in which I show you how to install and run a program on Python, I'll do this very thing. But keep in mind, in that situation, I don't have a situation where I know what it is I'm intending to do. If you know that you're trying to do a specific thing, like store a count, store a sum, store an average, store an age, then use variable names that tell you that. And it really doesn't take that much more time to do that than just write A, B, and C. One of the things I like about Python is it forces you to indent to match the programming logic. In Python, it knows that when I wrote for value in some data, and then I indent some and indent this print line, this loop, which is what this is, consists of these two lines of code. Every time this loop repeats, it's executing these two lines of code. But print here is at the same level as for, so it's not part of this loop. If I were now to indent this to the same level, it would be part of the loop. Some programming languages don't force you to indent to match the logic, and therefore it makes code more difficult to read if people don't indent to match the logic. And also notice the white space. I like to do things like this. Here I'm creating some variables, white space, doing something, white space, doing something else that's a unit. These three lines go together. They're separate than this, and they're separate than this, so I don't indent here. White space. That's how I choose to do it. You can have your own logic, but if I take out each blank line here, the program will still work fine, but it's difficult for me to look at the code and understand that this is a section that's supposed to do one thing, this is a section that does something else, and so forth. Think of it as being like white space that's used in books or section headings or whatever. It's there to help the reader. It doesn't change the underlying information. Because Python forces you to indent your code to match the logic, I can't show you how not to do it and have something that works. But I can show you in the C programming language. So here's a C program that works. And the computer has absolutely no problem understanding what this does. The problem is, I have a problem as the human reading it. Even though I understand how to program in C, it's difficult for me to read this without literally going through and saying, oh, there's a semicolon, there's a semicolon, there's a semicolon, because the semicolons terminate lines in C. Here's my loop, oh, here's some curly brackets, there's closing curly brackets. What am I doing here? Well, it's really just this program, but written in C. But there's no white space or indentation used here to make it easier to read. So what I'd rather do is this. Now this looks a lot like this, right? Except for the things that are specific to the language. I have to have semicolons at the end of lines. Loops don't require indentation, so we use curly brackets to represent the body of the loop. And that's what I've done here. This opening curly bracket matches this closing curly bracket. This opening curly bracket matches this curly bracket, and so forth. This is indented to match the logic, and I've also used white space to make it more readable. But this program, this version, works exactly the same as this version. It's just that this is easier for me as the human to read. That's why I do it. As your program, dealing with bugs is going to be a way of life. That's just the way it is. So things that are wrong in your code are called bugs, and the act of tracking those down is called debugging. And so I also put it down here, finding and fixing bugs is debugging. I should debug that and not had it twice, but I didn't. So bugs can be placed in one of two broad categories. Things that are syntactically wrong, which we call syntax errors, and logic errors. So syntax errors are like grammar errors in a spoken language. There are explicit rules of grammar, and when you violate those rules in a given context, we say that you made a mistake. So look at this code here. I say I'm selling price is 100, cost is equal to 40, and then I say if the selling price is greater than cost, print you're rich. But when I try to run this program, I get this syntax error message from the interpreter. And it points, see the little caret here, it's using it as essentially an arrow to tell you where it thinks, and it is correct in this case, but where it thinks the mistake is at. This is invalid syntax. So what's wrong with that? Well, this if statement here should have been terminated with a colon. And so because I left it out, the interpreter catches that and says, you're doing this wrong. So it can help me out there. And this type of thing will happen a lot. You'll do it when you're writing code. I do it when I'm writing code. As you watch my videos, you will see that occasionally I'll do it, because if I had to create perfect videos, I wouldn't create any videos. So most of my videos, or at least this way, many videos will include some errors. And in many cases, I just leave those in the video and post them. So if nothing else, they show you I make mistakes too, and they also will at least give you some experience in dealing with errors and tracking them down. Logic errors, though, are much more difficult to track down, because suppose you wrote this, answer equals 2 times 3, but the formula you're supposed to use is 2 plus 3. The computer can't help you here because this is legal. There's times you really do need to write 2 times 3 is equals 6 instead of 2 plus 3 equals 5. So this is a problem of logic. This is syntactically legal. This is syntactically legal. The way you know there's a problem in most cases is you just get the wrong answer, which is why you also should check your answers as much as you reasonably can. Now, in some cases, logic errors lead to what we call runtime errors, which is when you run the program, then they cause the program to crash in some way because your underlying logic was wrong. But you can't always count on that. So you just have to learn to debug, and once again, this is why you should check your code with known answers. So I may not always hard code something like this. Maybe I did this just to see if answer at the end would be correct. And maybe I'm gonna do a bunch of things with the answer, but at the end I want to see if the final answer is the same as what it was here. And if I get to the end and I get answer is equal to 12, but it started with 5 and I know it never should have changed, that would be my clue that I made a mistake. So that would be one way I would test my code. So how can you be successful trying to learn to program? I think there is no replacement for reading and writing code. But of course, if you're a beginner, it's difficult to know how to write code, because if you know how to write code, you wouldn't be watching my videos, right? So one thing you can do is get code that already works and just run it. And try to understand the logic and say, oh, I see what this does, I see what that does, and try to see how it works. Like you may go back to what I have here and say, well, what does this look like it does? Here's the Python version. Oh, well, this is a lot of things we haven't seen yet, but you'll eventually learn this is a Python list, and we'll call it sum data. Here's a summing variable with an initial value of 0. Here's a print statement. Here's a loop. And it's going through this loop, repeating this value over and over again, and finally printing something. This code works. And so you could run it and see what it does. Things like that. Modify code to see how it affects the results. So you may want to do something, because I've had things that I typed up and want to see how it worked. And let's say, for example, in these slides that you're looking at over here, this is a PDF, but I created it using a typesetting language called LaTeX. And tau, epsilon, chi, right? So on a computer, typically we would write what looks like latex, but in reality it's LaTeX. It uses these Greek characters, right? But I don't have Greek characters on my keyboard. But it uses plain text, so I can use a text editor to type things up, and then ultimately I turn it into PDF. Well, sometimes I find code online and it places something. So it may say that, indent equals, 0.14 inches. And I may look at what I produce and think, wow, that doesn't quite look right, but I don't know what to do with it. So I take the code and maybe I change it to 0.20 inches. Or they may have units. They may I at least understand inches, but they may actually write it like this, 0.37 units. Well, I don't know how big a unit is, so I really don't have a good feel for what that does. But if I start messing with it and change that now to 0.5 units, say, oh, well, now it looks like it's getting closer to what I want, and I can compare how much I changed this to how much it changed on screen and get a better feel for what this line of code does in the first place. You can do the same thing, exact things with a program. Take something that I created and change the numbers. So if we went back up to this, maybe you go in here and add some numbers and run it again and see what happens, or delete some numbers and run it again and see what happens. So you're starting to create this cause and effect relationship. But another thing that can be helpful is deliberately break code, so you start to see error messages under controlled circumstances. When I would teach programming languages in the past, I'd have students contact me And maybe all they did was send me their error message, and it would say something like error 14. And while I appreciate their confidence that I knew what error 14 meant, I don't actually know what error 14 means. So the easiest way for me to debug code is to take the existing code, run it, see what happens, and then start trying to fix things and see the cause and effect relationship myself. So that's a basic debugging skill. Hopefully the tool can try to help you, like in, where was it at? This case, it was correct that this is where the error was at, but these tools aren't perfect, so sometimes they leave you astray. But at least I would have came back and looked at this line and said, well, what looks wrong with this? And maybe what I would do is comment out this line and then rerun the code and say, oh, now it works, so maybe this really was the problem. That's still not necessarily a guarantee. But now if it still has an error, maybe that makes me think this wasn't the problem. There's lots of different possibilities when you're debugging, and I can't tell you exactly what to do, but that's an idea. So I'll do things like that. And then finally, write small programs to test concepts. If I've written a 200-line program and I want to add some functionality to it, but I'm doing something that I'm not familiar with, maybe instead of putting the new functionality in the entire program, I may write a small 10-line program that's supposed to do whatever that functionality is, like using a new language element I've never used. And I do that to isolate it from everything else so I can better understand what it does. Because as I have more lines of code, I don't know how much of what I see is being caused by the other lines of code and how much is being caused by the new language element. So I want to narrow it down to just that small thing. And then I save those programs. On this computer here, I have literally hundreds of small programs I've written over the years to do different things. Because maybe it took me a while to figure out how to make that concept work. And then if I don't use it for another year, I may have forgotten exactly what I did. I remember I've done it, but I can't remember the details. So I go back and look at my own code and say, oh, this is what I was doing. So I spend 5 minutes looking at it a year from now instead of spending an hour figuring it out from scratch again. So it's helpful in that case. So these are the things I think you need to do. But ultimately, all these things come back into writing code. And if you can find other people's code, not in your homework, not homework in your class where you're copying off somebody and cheating, but finding examples of code online and trying to better understand what other people did to make certain things work is helpful. So if you found what I've said helpful, then stick with the video series and learn how to actually do things. We'll learn language elements, and then throughout the video series I will also add application videos in which I'll have a problem and then say, how do I think about this problem, and then turn that into code. And some of those will be real world problems that I just had to deal with, but other things I have to make up, because especially in the beginning, when you don't know many language elements, you can't really do much other than add some numbers together and ask some questions about those numbers and things like that that aren't really plausible in terms of why I would write a program. But the alternative is waiting until you've learned a whole bunch of things and then you start writing code. But then I would argue you don't really know those things as well as you think, because if you've never written code to do them, you think you know how to do certain things, but you haven't discovered that you really don't know how to do them. So anyway, stick with the video series and learn more.